Okay, welcome everybody to this month's installment of the Chalmers AI for Science seminar. Today we are very pleased to have Michele Ceriotti from the Polytechnic of Lausanne, the Federal Polytechnic of Lausanne, to present his work here. Michele has a background originally from University of Bicocca in Milano, material science, then went on to do a PhD in physics, working on colored noise integrators, right, for MD, and graduated in 2010, right? And then 3 years at Merton College in Oxford. And then since 2013, he's leading a group where he is now and happily conducting exciting research. So we're very happy to have you here and welcome.
Thank you. And thanks everybody for coming. So as you will see, there is a lot of tension in this talk and in my research over the past year or so between should we put physics, some physics, much physics, no physics, and trying to find kind of an evidence based way what is the right balance between giving in to data will solve it all and still trying to put physics at the center of what we do. So okay. So just to give a little bit of background, I think that probably many of the people in this room do stuff very similar to what I do in the big scheme of things, at least. But my background is really in molecular dynamics and atomistic modeling, and so I've grown up with this idea of modeling as something that would go from understanding the behavior of atoms at the scale of the atoms to building up a predictive model that would eventually give us the prediction of better materials to make airplanes or the prediction of better drugs to cure disease. And the idea is that by starting from the infinitely small, we gather so much insights, but this is very slow. And the reason why this is slow is that even though, of course, we know pretty much exactly the fundamental equations that govern the behavior of the atoms, in practice it's not really feasible to do that, because if you want to exactly describe the behavior of the electrons, you have to go to very computationally heavy correlated post-Hartree-Fock methods. And if you want to describe the behavior of your molecule in the horribly complicated goo that is the cytoplasm of a cell, you also need to take into account the disorder, thermal fluctuations, all kinds of environment effects, which require you to sample over and over the properties of different atomic structures. So the idea is that what I would like to do is to use machine learning to make all of these fast, or at least faster. And so this is, in a way, I see it at least as not in opposition, but in contrast with an approach which is also very reasonable, which is to go straight from the simplest possible description of your physical system to a prediction of what it will do when you try to use it to cure cancer. So the idea is still to go through the bottom-up modeling steps of understanding structure, the properties of a structure, the thermodynamics of a structure, and eventually understand the mechanisms, but making it fast. And so if you want to make something faster, you should focus on the bottleneck of this whole machinery. And if you start from first principles, from a description of the electrons, the bottleneck is clearly the quantum mechanical part, especially when you scale up to large systems. So the idea is that rather than using an approximate form of the Schrödinger equation to compute the energy or whatever other property of a system, we use a data-driven surrogate model to make this prediction. And so when we do this, I think it's very important to keep in mind that we are still building on top of a modeling protocol. So we are substituting one way of computing these properties with another way of computing those properties. And given that the physics-based way involves a sequence of different steps, it always makes sense to keep in mind that you might choose not to throw away the physics entirely, but to only substitute some of the steps within this workflow with a data-driven alternative. And another important thing to keep in mind, and I will return to this, and this also sort of touches upon the software development efforts in the lab, is that not only you have sort of a modular intellectual framework with which you interact, you also have software updates that need to be run right now. You also have on a software stack that is a mess already, and we are making it even messier by injecting machine learning into it. So before I start delving into the more sort of analytic look at the structure of the models, at the structure of the software, let me start, forgive me for starting with a grand overview of all the fantastic things that machine learning can do for you. Okay? I hope you will forgive me. So I really, I don't know where to start. Even just in my group over the past 5 years, we have done at least a dozen completely different applications to materials, energy materials, silicon, organic molecules, something vaguely bio-y. And so I have chosen a couple of examples because I like them and because I think that they are also kind of instructive. So the first one, to give you context, this was coming from a collaboration with BASF, the chemical company, and they wanted to understand better high entropy alloys to be used as catalysts. So basically they came to us with a list of 25 transition metals, and they wanted to be able to do every possible combination of these 25 elements. Now, you should know, and I'm realizing that this is not anymore the case, that traditional ways of building machine learning potentials at atomic scale treated each atom as a completely, each atom type as a completely different entity. So if you want to learn the interaction between scandium and titanium, it's a completely separate beast, the interaction between scandium and vanadium. So this means that when you want to build a model that works for 25 elements, the complexity grows combinatorially with the number of species that you consider. So the idea that we applied here, that in retrospect it's essentially what every graph neural network does by attaching tokens to the atomic species, but was basically, I think it's also instructive in terms of interpreting this tokenization mechanism. Essentially, we went back to the Greek, but every culture has something like this. Essentially interpreting the behavior of the different atomic types as the combination of the behavior of a small number of, let me call them, alchemical pseudo-elements. And essentially the model now doesn't learn the behavior of carbon, boron, and nitrogen, but it learns simultaneously the behavior of fire, earth, and water, and the compositions of carbon, boron, and nitrogen on the basis of these 3 alchemical pseudo-elements. Now, this works very well, but what is interesting is that if you do this exercise for these 25 elements, now you have learned for each element a vector of 3 number that gives you the decomposition in fire, earth, and water. So how do these vectors look like? And what I think is really, really cute is that just through learning a potential, we basically got a distribution of the chemical elements, an embedding of the chemical elements that reflects the structure of the periodic table. Now, if you know a little bit about history of science, the big breakthrough with the periodic table was not so much recognizing that the behavior of elements has some periodicity, but the fact that there were holes in the Mendeleev periodic table that were then discovered to be elements that had not been discovered yet. And if you look here, and if you know a little bit the transition metals, you notice that there is a gap between tungsten and iridium because BASF didn't care about osmium and rhenium for some reason, and so we didn't include them in training. So we tried to do something crazy, basically just postulate that the alchemical embedding weights of rhenium and osmium would be somewhere linearly interpolating between tungsten and iridium. And this model predicts rhenium and osmium pretty well. And so to me, what is the reason why I'm giving this example is that I think, well, first of all, it's cute, and second, it emphasizes how the concept of interpolation or extrapolation that we often use to say whether a model is good or bad is not absolute, but is relative to the representation that we choose for our problem. I could easily convince you that making a prediction for an element that I've never seen before is the ultimate extrapolative exercise, but through the alchemical embedding that I have chosen, this is literally a linear interpolation. And then, I mean, this works well. We can simulate a soup of 25 elements, look at local ordering, look at how different elements have a preference to segregate at the surface, which of course is important if you want to do heterogeneous catalysis. Now, completely different example, a ferroelectric material. So, lots of physicists, so probably you know what's a ferroelectric, but for those who don't know, a ferroelectric is basically the electrical equivalent of a magnet. It's a material that develops spontaneously an electric dipole. And barium titanate is particularly interesting because as you change the temperature, it goes through a sequence of phase transitions to different ferromagnetic ordering. So barium titanate has been sort of the poster child of DFT. It's been studied to death. And if you want to study barium titanate with electronic structure methods, it's kind of complicated because this macroscopic polarization comes from the correlations in the distortions of the lattice that occur at the atomic scale, and these distortions have very long-ranged correlations. So in order to describe barium titanate well with DFT, you have to first do the simulation in a small box, which is all that you can afford with DFT, and then fit an empirical model of the interaction between these little dipoles so that you can make the statistical mechanics on a larger length scale. So what a machine learning model gives you, especially a machine learning model that gives not only the energetics but also a prediction of the polarization, is that, well, you can compute properties that are actually fairly complicated to extract, that involve dynamical and thermodynamic sampling of the correlations between the dipoles, and you can really scale up the simulation size by brute force to the point where you can observe this is a representation of the chains of correlations between the dipoles that are very long-ranged, and you can basically study the convergence of the different phase transitions as you make the box larger and larger, and you don't have to worry about doing these, the approximations that you introduce by fitting these empirical models. Now, another example that I want to give you that touches upon a slightly different section of our research is really getting into this idea of blurring the lines between doing models based on machine learning and models based on quantum mechanics. And the first example that I want to give you that is relatively simple is that of predicting the behavior of matter in extreme conditions. You want to study hydrogen in the core of a brown dwarf. You have a temperature which is of the order of several tens of thousands of Kelvin. And at that point, you cannot anymore assume that your electrons are stuck in the lowest possible energy state. They will also be thermally excited. And so if you want to study hydrogen in these extreme conditions, you need basically to work not with the ground state energy, but with something which is called the Mermin functional, which is electronic free energy, essentially. And now, if you think about what this means in terms of training a machine learning potential, it means that now, for each electronic temperature, I would have to train a different machine learning potential. So what we did instead was to exploit a physical approximation of the Mermin functional that requires only the ground state energy and the ground state density of electronic excitations. This is basically the distribution of the possible energy levels of the electrons. And then we just learn these two ground state properties, and by combining them, we can make a prediction at any electronic temperature. And so we can run simulations up to 50,000 Kelvin that predict very well the same behavior that we would have with a dedicated MLIP. And this is a first example of how, you see, we take an expression. This expression is physics-based. We choose two ingredients that we machine learn, and we combine them with a perfectly legitimate physical expression. Second example, let's say that you want to learn electronic excitation energies. So not just a sort of this thermal average, but specific electronic excitations. So one way, very approximate way, but nevertheless, one way of getting electronic excitations is to compute the Hamiltonian that describes electrons in a molecule at an effective single particle level. Apologies for those of you who have no idea of what I'm talking about. But basically, you need to compute a matrix and then diagonalize that matrix. And the eigenvalues are related to the excitations of the electrons. So one thing that you could do is basically build a model of that matrix. And then you train your model to match this matrix. But nobody really cares about the matrix itself. We care about the excitations. And so what we can do is instead minimize a loss that only depends on the value of the eigenvalues of this matrix and not on the elements of the matrix itself. This is very helpful because this machinery is not as expensive as solving quantum mechanics, but it's messy, it's complicated, and it does cost far more than a potential. And so you don't want to have to use a very large matrix here. But if you want to converge the quantum mechanical problem, you need a large matrix, you need a large basis set. And so what you can do here is that you do the quantum mechanics with a large basis, and then you fit a matrix that only tries to reproduce the interesting excitations that can be represented with a small matrix. And this works very well. It's very transferable. We can train the model on different conformers of just these 7 small molecules. And we can make predictions for molecules that have completely different topology. We can make predictions for much larger molecules. We can go to the limit of large conjugated systems. We can predict beta-carotene. And so the message here is that by choosing at which point we inject the machine learning and which point we rely on the physics, we can get a model that is more robust and extrapolates better. Now, having hopefully convinced you that there are a lot of interesting things that you can do with machine learning for chemistry and materials modeling, let me get to another thing that has kept me and has sort of sacrificed the lives of innumerable PhD students and postdocs, which is trying to answer the question, what the hell are we computing here? We know what physical models compute. What are we computing with machine learning exactly? And so the idea is a little bit to look into the machine learning model and try to understand what are the ingredients of a machine learning model, understanding how to combine them so that you can basically mix your own. And one thing that became very apparent as soon as we started sort of looking critically at the structure, the mathematical structure of the models, is that since, I think it's fair to say that even though it has now become very fashionable as a computer science conferences are now full of applications to materials, but this stuff has been started in the physics and chemistry community almost 20 years ago. Okay? And so this was done by chemists and physicists who were trained into really giving a lot of importance to symmetry. And so the symmetry of the model is really a sort of organizing principle to understand a lot of the early developments in this field. And back in 2021, I made this figure that was basically trying to classify all the, the jungle of acronyms that was emerging in the field in terms of how these different models incorporated symmetries, fundamental symmetries of the mapping between a structure and its energy. And it turns out that these, the role of symmetry runs extremely deep, and that even if you look at equivariant neural networks more or less explicitly, because of course you can always remassage things and make them look different, but deep down all the models rely on the same structure. First, you describe atomic environments. Why atomic environments rather than entire structures? Because then it's like learning the Lego blocks that can build up any system. So you don't learn the whole, you learn the parts so that the model extrapolates much better. Again, it extrapolates better because it's not really extrapolating. Since your building block is just an atom-centered environment, building a complicated structure from these environments is not an extrapolative task. You are interpolating between the different possible environments, and the extrapolation comes from the structure of the model. And then you build in permutation symmetry by describing these environments in terms of an expansion of the neighbor density on some basis functions. Since you sum over all the neighbors, your descriptors don't depend on the order by which you list the neighbors. So permutation symmetry is built in. And then, in order to incorporate rotations, one thing that you can do is you pick as the basis the spherical harmonics. Why? Because the spherical harmonics are the objects that transform in the simplest possible way under rotations. Now, if you take these and you try to build a model on these, the problem that you face immediately is that if you want to learn the potential energy, which is a scalar, so it doesn't transform under rotations, the only terms that you can keep are the terms that are invariant under rotations. So how do you build something that transforms like a scalar but has more complicated information? It turns out that symmetry ties your hands, and the only way that you can combine two irreducible representations of the rotation group and obtain another irreducible representation of the rotation group is to use an expression that looks a little bit horrible, but you see it's a product of two sets of descriptors with some coefficients. They are called Clebsch-Gordan coefficients, and they tell you how to take two terms that transform like scalar or vectors or tensors and give you something that transforms like a scalar, tensor, or vector. And this is essentially the only way you can build a model that goes exclusively through a series of irreducible irreps of the rotation group. Now, the problem is that since all the models have this same very mathematically constrained structure, they also suffer from the same pathologies. So, for example, let me go back a second. So this horrible figure is basically telling you that you can do this thing iteratively, and that each iteration, your model will spit out descriptors with different character. And in particular, will spit out some descriptors that are invariant. And so one thing that you could think of doing, and actually what was done originally, 2007 by Beller and Parinello, is to say, well, let's just stop this iteration at body order 3, and we throw these invariant descriptors into a multi-layer perceptron. So I will get a universal approximation of the properties using only these. And the problem is that this doesn't work because these body order 3 invariants do not distinguish between distinct environments. Basically, you can find, and Sergei here found, this geometric construction of some spatial arrangement of atoms that have exactly the same three-body correlations, meaning that no matter how sophisticated is your model downstream of these three-body descriptors, it will make the same prediction for those environments, even though their true properties are different. And this actually really hurts because a good model is a smooth model. And this means that this will not only hurt your ability to predict these specific weird arrangements of atoms, but also everything in the vicinity of these weird arrangements of atoms. So we have a solution to this problem within this same sort of intellectual framework, which requires, however, to work with fundamental building blocks that are not atom-centered environments, but triplets of atoms. So this allows you to build a deep set architecture that gives you a complete symmetric representation, but is a little bit of a mess. So an alternative is to say, well, whatever, why stop at body order 3? I can go up to arbitrarily high body order. Now, if you want to do this, actually this is extremely powerful. You get a complete polynomial basis to expand any property. The issue is that the number of polynomials that you need to consider grow exponentially with the body order. So you need to build in some kind of contraction that keeps from this exponential increase in complexity. Or, if you are Filippo, you can do something else, which is to basically do a kernel trick, essentially. So if you do a kernel trick, you can build kernels that are equivalent to this body order polynomial expansion by computing the polynomial descriptors and then for two structures and then taking a scalar product. And what you can do is actually build these kernels in an alternative way that doesn't require you to do the expansion in the first place. So essentially you can go up to arbitrary high body order by building this hierarchy of symmetric kernels rather than a hierarchy of symmetric descriptors. Again, very elegant. I really love this paper, but it's a mess. You know, nobody uses it. I'm very sad, but it's true. And then even you solve this new problem. All of these descriptors are predicated on expanding the environments up to a certain cutoff. Now try to learn long-range electrostatics with this. Electrostatics, you know, sorry for the fancy units, these are atomic units. So up to 50 angstrom in separation, the interaction between 2-point charges is still 10 millihartry, which is like almost 300 millielectron volts and 10 kilocalorie per mole, I think, or something like that. Maybe 20 kilocalorie, I mean, a lot. So we have come up with a solution again within the same intellectual framework, which is based on expanding, rather than the atom density, some kind of atom potential, which effectively can be seen as solving the problem in Fourier space. Again, you know, this works. We can build models that work very well based on this general idea and that they are equivariant. But then, you know, you read this, I think that probably everyone here has read the bitter lesson essay. If not, just Google it. It's half a page and it's really sad and it's probably very true. And so Sergei, still Sergei, he has a dual degree in computer science and he was like, you know, man, why do we bother with all this mess? We are learning on point clouds. People who do point clouds for shape recognition don't do anything equivariant. They just augment the hell out of it. So essentially you take an architecture that is not bound to be equivariant and you just do augmentation at training time so that you learn equivariance from the data. And so Sergei came up with a, you know, honestly, you know, he didn't really put much thinking into it because actually this was meant for something else, just sort of a demonstration of something else. But he came up with this architecture, and the key ingredient is that it's built on a Cartesian basis, so just a Cartesian delta x, the Cartesian description of the edges, and it uses a transformer to do aggregation-free mixing of the edge descriptors, basically, or the edge tokens. And to my great disappointment, this works very well. It works better than most equivariant models on benchmarks, whatever that means. I'm not a fan of benchmarks, but still it's a piece of evidence. This works surprisingly well. And so this was made by a postdoc in the lab, and every time I show it, I wonder whether I should be offended by it. But this is giving a very, very strong evidence that maybe we don't have to worry about all of this complicated group theoretical stuff, and we can just let models learn equivariance and get away with murder. So, of course, since everybody is doing universal machine learning models that can be done applied to any system, we thought that we would also try to do this. But I was very unhappy with the data sets that are available because, there are hundreds of millions of configurations computed with electronic structural parameters that make absolutely no sense. And so instead, we try to think, okay, can we do a data set that is a little bit better thought out? We exploit the fact that we are in Europe so that we can call the data set maximum atomic diversity without getting our grants killed. And then the idea is to have a data set that is very diverse. We are not making a lot of work trying to get structures that are cleverly designed. We just try to get something which is really very diverse. For example, we do one thing which is pretty insane. We take real structures and then we assign the nature of the atoms completely at random. So you can get, I don't know, sodium chloride, but now you have fluorine, hydrogen, xenon, plutonium, and praseodymium. And so we end up with fewer than 100,000 structures, and really the key idea is that we try to diversify as much as possible. And then we combine this PET architecture, this MAD data set, and we try to train a universal model. And the result of this is that even though we are using only 100,000 structures, we are competitive in accuracy with models that are trained on 1,000 times more data points. And we think that the reason why is a combination of the diversity of the data, the fact that the electronic structure is done carefully and consistently, and the fact that the architecture is more expressive thanks to the fact that we don't introduce these rotational constraints. So this works super well also in the extrapolative regime, so we can make predictions for different data sets, and we are competitive with the other data sets, with the other models, when we compare on the same on the type of structures that they are trained on. But when we look at truly extrapolative stuff, we actually end up doing much better. And the architecture is pretty fast, thanks to the fact that it is not constrained. And the only model that we tested it against that is faster is this orb model. And I will return to this orb model later. This orb model is not only breaking rotational symmetry, it's also breaking energy conservation. And I will return to this. So most importantly to me is that this doesn't only perform well on benchmarks, but we can use this to do real complicated simulations of the thermodynamics of materials. So we can compute, for example, the melting point of gallium arsenide. And I mean, the way you do melting point of gallium arsenide, or the melting point of any material for that matter, is that you do a simulation in which you have the solid in coexistence with the liquid. You compute the difference in chemical potential between the solid and the liquid. You repeat the simulation at different temperatures, and you find a point where the difference in chemical potential is zero. Okay? So we do this, and we get a melting point of about 1100 Kelvin. And now, what next? I mean, I have to tell you the melting point of gallium arsenide is 1500 Kelvin. So is the machine learning model crap, or is the DFT that we are trained on crap? So one way of doing this that takes time is to train a model specifically for gallium arsenide. then we can get the model much more accurate in terms of test set accuracy. And I mean, yeah, it's a little bit higher, but only 50 Kelvin higher, nowhere near. So this strongly suggests that the problem is the DFT. We can also do fine-tuning, but you know, if I have a universal model, I would like to be able to know whether it makes sense to just fine-tune or whether I should go for a better electronic structure reference. So it would be ideal if we could just run with PetMud and get an estimate of the error. And luckily we can, because the model also builds in a shallow ensemble architecture. So basically we can make, at no additional cost, we can make 50 predictions for each evaluation. And we can use these together with some reweighting techniques to get basically an ensemble of predictions of these chemical potential curves. And so essentially from a single trajectory we can estimate that our result is with an error bar of plus minus 50 Kelvin, which is of course in very good agreement with the actual error, and sending a clear message that the problem, since the error is about 500 Kelvin, the problem is with the reference and not with the machine learning fitting. So now, one message I want to send very, very clearly is that when you break physical symmetries, you have to be very careful. So you can go and look up the story. This is a paper from 2007 that you see got published on the Glossy Press. And they found that if you would run a simulation of these, 2007 was, the hype was nano, no? And so you create this nanostructure, you put some charges around it and water, and you create a diode for water. So water only runs preferentially from bottom to top and not from top to bottom. The reviewers had nothing to say about this, but clearly this breaks symmetry and the second principle. And a few years later, they discovered, another group got sufficiently pissed by the fact that this got published, that they ran this carefully and discovered that essentially a combination of using a Berenson thermostat and compiling GROMACS in single precision was breaking symmetry. So the message here, I hope that my name will never be on a slide with this story, okay? So it's very important, you break symmetries, you have to be careful. So we tried to look carefully at whether we can trust the results of these rotationally unconstrained models, because they get very close to being invariant to rotations, but they are not invariant to rotations. And so one thing which is nice is that it's very easy to verify whether the model is breaking symmetry, because you can, at inference time, make multiple predictions for different rotations and summing them up. And there is something which is called Lebedev grids, which are very sophisticated, as the Russian name implies, and that basically cover uniformly the space of rotations. And you change nothing in the architecture, but you can make it as equivariant as you like. And the bottom line is that for many different properties and actually many different systems, we find that running the simulation with the approximately equivalent model or with this posterior augmentation, basically nothing changes. If you want, now the problem here is clearly you can do this as a test, but to converge these grids reasonably, you need about 20 rotations. So the red curve, the black curve is 20 times more expensive than the red curve and nullifies the whole point of doing an unconstrained model. So what you can do instead, if you run MD, is that basically, well, there are two things that you can do. One, and I will return to that later, you can do multiple time stepping, so you do this rotational correction only once in a while. But the other thing that you can do, which is even simpler, is that while you run MD, at each time step, you evaluate your energy on a different random rotation. this basically transforms the small bias that you might be getting from the lack of equivariance into a tiny random noise that slightly breaks energy conservation, but very, very, very slightly in a way that you can easily fix with a weak thermostat. So basically, you can, there are ways to run this stuff safely. You have to be careful, but you can run this safely, and there are big advantages in doing this. Now, let me go back to ORB, this model that was not conservative. What does it mean? Well, so to do molecular dynamics, you don't need energies, you need forces. The forces tell you how your atoms move. And how do you get these forces? Well, as a self-respecting physicist, you take a potential, you differentiate it with respect to the atomic positions, and you get the forces. But you could also predict the forces directly as the output of your model. And why would you do this? Well, you would do this because it's about 3 times faster. And indeed, we can build on top of our PET-MAD model a head that predicts forces non-conservatively, and hop, immediately we are as fast or faster than ORB. So is this a good idea? No. So the problem is that if you predict forces directly, not only your forces are not the derivatives of the potential, they are not the derivatives of any potential, which means that essentially energy is not conserved. Not just the energy associated with your potential, but there is no conserved energy, meaning that if you try to run a constant energy simulation, the kinetic energy in your system will drift away. And this seems benign, but if you map it to human quantities, your system is heating up at a rate of several billion Kelvin per second. So it's really massive. So another important thing to stress is that this is not just a problem of our implementation or of ORB. Any model that is non-conservative will exhibit this uncontrolled drift. Of course, the more you are training against conservative forces, so the more accurate, the slower this drift will be, but you can't run long-term stable dynamics, basically. So one thing that you could think of doing, and one thing that usually people who use direct force predictions do, is to use a thermostat, which is something I know 1 or 2 things about because I did my PhD on this stuff. Is basically something that allows you to equilibrate, get your system to equilibrate with a heat bath. And so in a way, you can expect that by doing this, the energy that is injected by the non-conservative model will be sucked up by the bath. And it looks like it works. This is the same drifting trajectory as before. I add a thermostat, and everything fluctuates around 300 Kelvin as it should. But now if I look separately at the kinetic energy of the oxygen and the hydrogen atoms, oops, they are equilibrating at different temperatures, because the thermostat is only forcing the total temperature to be right, but not the temperature of each degree of freedom in the system. So at this point, basically, I had already written the first draft of the paper saying, okay, this direct force prediction is garbage, don't do it. But then, thinking about it a little bit more, if you have a model that predicts the forces directly as well as the potential, which doesn't cost you anything because you share all the expensive part of the architecture, anytime you like, you can always get conservative forces by differentiating the potential that you're computing anyway. When you do that, you pay a factor of 3 overhead, but you can choose when to do it. And this can actually be extremely useful. First thing, when you train. When you train, you can start training your model using direct force predictions, and after a while, you switch on computing also the conservative forces, and you add them to the loss. And for reasons that we don't understand fully, this converges in terms of actually, not in terms of epochs, but in terms of overall cost, more than 4 times faster than doing a conservative training from the get-going. And also when you do inference, so when you try to do random molecular dynamics, you can also use this by doing this technique that is back from 1992, which is called multiple time stepping. So the idea is that you run molecular dynamics with the direct force predictions, and then every 8 steps, you do one correction that requires you to compute the conservative forces to do the backpropagation. And this correction cures completely the energy drift that you get within conservative forces. But since you compute the conservative forces only once every 8 steps, you have basically 90% of the speed up of direct force predictions. So even though we started writing this paper with the intention of trashing the idea, I actually find myself using a lot direct force predictions because, if you are careful, they can be extremely useful. I mean, a factor of 3 speed up is not something I would risk effing up completely my simulations. But if I have one way to fix it, then why not? 3 times faster is a nice speed up. And I want to stress that this is not something that requires a lot of care. It's something that you can do out of this PET-MAD universal model quite easily. So we picked a system just because somebody gave me a starting configuration. This is a ionic crystal, ionic liquid. And if you run with this with a direct force prediction, blows up immediately. If you put on a thermostat, it looks like it works well, but then actually your chlorine atoms are equilibrating at 2000 Kelvin. So really, don't use direct force prediction on its own. But if you do the multiple time stepping trick, everything works well, you get the right structural and dynamic properties, everything works super fine. So really usable and, in my opinion, to be used. So right now we are trying to push these in different directions. One is just trying to scale up these unconstrained models because, yes, we can train them on small data sets, but eventually they will start making huge data sets with the DFT references that make sense. And so we want to check how the models scale, and it actually performs very well in the high data regime. The unconstrained architecture allows you to play around with how you allocate the parameter budget, and this allows us to make very large models that are still very fast. So we can get models with 20 times more parameters than ESN and still a factor of 5 faster. And so I think really that the big advantage of these unconstrained architectures is that you can play with them without being constrained by all of these symmetry requirements. And another example of how you can play with these architectures very easily, and this again is an idea mostly from Filippo Bigi. So the idea came about because these direct force predictions use these forces that are not physical, and I mean, okay, they don't work great, but they kind of work. And so Filippo started thinking, okay, but what if we avoid computing forces altogether and we just take position and momenta at time t and we predict position and momenta at time t plus delta t? How far can we push delta t? And the architecture of the model was super easy to do because the only thing that Filippo did was adding the atomic momenta as additional node descriptors. And we didn't have to worry about, wait a minute, now I have a vector that must transform covariantly together with the edges and then just 3 Cartesian coordinates, chuck into a transformer and see what happens. And what happens is that this works very well. Not only we can train a model that works for, I don't know, liquid water, we can build a single model that you can apply to, lithium diffusion in battery materials. MD time step of 2 femtoseconds predicts a superionic transition at about 600 Kelvin. Flash MD with 8 times time step predict the transition. Yes, it's not exactly the same temperature, but I assure you that if we change the cutoff of the DFT calculations, it would have changed the transition temperature by more than this. Alanine dipeptide in water, okay, ignore for a moment that this is based on PBE. So in order to get water that is not glassy, we have to go to 500 Kelvin. But if you ignore this, which is not the fault of FlashMD, we can run FlashMD up to 16 femtoseconds and get a free energy surface for solvated alanine dipeptide that is essentially the same as that run with MD. This is a simple but very funny system. This is the 110 surface of aluminum. It has this surface pre-melting, and the surface starts having some fancy dynamics close to the melting point. And again, we can push this to 64 femtoseconds, and the qualitative behavior of this transition is perfectly captured. And so what is nice about the way we designed this is that since we are predicting a deterministic constant energy trajectory, we can build samplers for any ensemble just by chucking the FlashMD module in between thermostats or barostats or whatever. So in a way, this goes very well with the modular design of the integrators. We can enforce energy conservation essentially by every time we do one FlashMD step, we rescale the velocities so that the total energy doesn't change. And this, of course, by construction fixes the energy conservation. Okay, I apologize, the paper has the figures. It brings in similar problems as the thermostating of the non-conservative forces. So this has a tendency to break equipartition. And the hypothesis was that the reason why this breaks equipartition is that the model is not symplectic. If you don't know what symplectic means, I don't think I have the time to explain it. It's basically a geometric property of Hamiltonian dynamics, of constant energy dynamics, that is preserved exactly by the MD integrators, but not by this architecture. So Filippo came up with an approach that actually makes it possible to do a long time step integrator that is exactly symplectic. And it's also very, very elegant. I really like the formulation because it's based on learning the classical action. The action is basically a sort of alternative formulation of dynamics. It's a central quantity of a formulation of classical dynamics. And so learning this quantity that corresponds to an action, you can build a propagator that is exactly symplectic, even though it's based on a machine learning formulation. And the slight issue is that the way it works is that it requires computing this action function halfway between, in the middle of a time step. And so this means that basically you have to do an iterative procedure in order to converge it. Now, if you run this iterative procedure, you actually get perfect energy conservation, perfect equipartition, everything gets fixed. So it's very clear that symplectic behavior is an extremely useful property to have. And the problem is that you need to do like 32 iterations, which is more than the number of MD time steps that you are avoiding. So, full disclosure, this is beautiful, super elegant. I think giving a lot of insights about the issues with a predictor for molecular dynamics, but as of today, not very useful. Still, you can run complicated. This is a simulation of the relaxation of a germanium tellurium glass. Very subtle effect. This is basically, you see, it's a logarithmic relaxation of the potential energy. It's a typical behavior of glassy systems. And FlashMD already does a pretty good job on its own. So maybe it's not a bad idea to get a qualitative insight on your materials. And if you prepared to run 16 iterations of the symplectic integrator, then you are on top of conventional MD. So let me wrap up quickly. So the take-home message here is not that you can disregard physical symmetries, but that even though these are important, there are physical constraints that can be learned easily or worked around by simple tricks. And what you gain by dropping a rigid enforcement of these constraints in the architecture of the model is a better allocation of computational budget. The jury is still out, but there is evidence that you also get more benign learning dynamics. And in general, it's so much easier to play around with these things if you don't have to worry about how the different ingredients in your model behave from a symmetry perspective. I also sort of a shout out to the metaverse. So we are doing a lot of work trying to have sort of a modular software stack. I know that many people here are also invested in software development. I think it's a highly underappreciated endeavor. And so we are trying to do this in a way that doesn't sort of create a monolithic software, but we try to have different components so that if you only need an MD engine, you can take only the MD engine and use your own potential. Actually, it's very easy to put new potentials into this meta. If your potential can be exported to torch script, it's very easy to put it into a metatensor model, and then it can run on lamps. It can run. We are very close to having it run on Gromax. So the idea is to have a sort of a wrapper that makes it easier to port models between different engines. And last but not least, this is basically what I discontinued my subscription to Netflix, and so now in the evening, rather than binge watching TV series, I am writing recipes. So this is a website on which, so because the weakness of a modular software ecosystem is that if you want to run a simulation now, you have to combine 5 different pieces of software. And there is really no good point in the documentation of these 5 pieces of software to tell you how to use them together. So the idea is that myself and also members of my lab, we are trying to build a collection of recipes that tell you, how to apply a thermostat, how to run path-integral molecular dynamics, how to do a simulation with non-conservative forces that doesn't blow up. And this is at atomisticcookbook.org. And feedback, pull requests, more recipes, very, very much welcome. So, of course, big thanks go to all the people who made all of this possible. Okay, I tried to already show the faces of the people who are most involved in everything, but everybody is contributing to the good fight. And so, with this, I also want to thank you for listening. And if you have questions, please go ahead. So we probably we don't do this, and so I think that if you wanted to do this is a common problem. So if you want to do IR spectrum of water, you need actually a time step of like 0.25 femtoseconds. Otherwise, you start getting into dithering. So in my opinion, the right way of doing that is that you run a long flash MD trajectory, and then you fire off 10 short MD trajectories with a finer time step, because the fast degrees of freedom are very easy to sample. So I think that in a way you need, yeah, it's much more efficient to do something like that than to try and interpolate between the large time steps.
But you would have to get into a cohesive trajectory somehow, I guess. If you do that, those two types of simulations, a fast timescale one and a long timescale one, you still need to get it into one cohesive trajectory, right, to do the Fourier transform without artifacts.
I think you can basically patch together the Fourier transforms and then.
Okay, yeah. Okay.
But yeah, this is something that I've been thinking about. I think it probably needs to be done carefully, but I don't think it's a super hard problem.
Okay,
thanks. Thank you. Regarding the PET model,
Yes.
why exactly does it have so much trouble predicting the forces? Because I might not remember, it's been a while, but Bela-Parinello networks and all these ACE flavors, they do well predicting forces.
Oh no, there is no problem in predicting forces. You can predict forces very easily, and you can train on forces very easily by just differentiating the potential energy. But this differentiation costs a factor of 3.
No, but I thought they're also directly predicting
No.
forces, no?
No model before the last 3 years, I think. Because actually, you know, the reaction of the physics community to realizing that you didn't have to implement all the forward derivatives yourself, but you could just do torch dot backwards, you know, oh my God, it was such a warm feeling that everybody just did that, no? But it turns out that it does have a factor of 3 overhead, and so there is no problem in predicting the forces. But these you can actually get very accurate predictions of the direct forces, but they are not the derivatives of any potential, and so.
Is that a problem?
Yeah.
As long as they run?
It blows up. It will eventually blow up because it doesn't conserve, and it's really much worse than not conserving, not being rotationally equivariant. Because if you're not rotationally equivariant, you do it round, you spin around, no? And you are back in the initial position. If you don't conserve, if you have no conservative forces, you do one turn and your energy has gone up about 1 millielectron volt. Another turn, another millielectron volt, and then this thing really blows up.
Can you make use of the knowledge that all the forces must add up to 0 without external force on the system?
You can do this. You can enforce it very easily, but that's not the problem. So in order, you can test. This is also the reason why it's hard, for example, to penalize for non-conservative forces explicitly. So you can test for non-conservativity by doing a loop, or the point-wise equivalent of non-conservative behavior is basically if you do for conservative forces, dFi over drj is equal to dFj over dRi, because that's the second derivative of the potential. If you do direct forces, you don't have this. So, but the problem is that if you want to test for this, dFi over drj is the Jacobian, and it's very expensive to compute. So in practice, there is no good. You are not saving any. It's actually much more expensive than doing the backpropagation, because now rather than doing one backpropagation, you have to do 3n backpropagations. Yeah. So.
Yeah, one more question from Esme.
Yeah, I was just curious about when you showed the example using melting of gallium arsenide.
Yeah.
You had these 50 different estimates.
Mm-hmm.
How, and I think you said that this was with no extra cost. So how does that work?
So essentially, this is something that we call shallow ensembles. The idea is very simple. Basically, you have you generate an ensemble only for the last layer weights. So all the ensemble members share the entire architecture and are only distinct by the last layers. So it's super cheap to compute them. And then what is not trivial, it's actually rather, so this gives you for free something like energy, the error on the energy of an individual configuration. If you want to do something like this, it's a little bit more complicated because you need basically, you have run one trajectory using the mean of the potentials, and you need to answer the question, what would have the sampling been if I had run with the kth set of weights? And this requires something which is basically a reweighting scheme, but can be done and it's cheap. It's a post-processing step, basically.
Very, very nice.
Thank you.
Since you're on that slide,
Yes.
because you show on the right-hand side, you show a solid-liquid interface.
Yeah.
And that is one way of getting the melting point.
Yes.
And on the left, you show chemical potential differences.
Yes.
Which is another way. So based on that, two questions. One is, which model you use for the liquid?
No. So this is a interface pinning. Yeah. So we get delta mu from a coexistence simulation. Yeah.
This is also the second question.
I have a question about the alchemical compression.
Yep.
Have you gone a bit deeper into it? Have you checked if this alchemical compression of the atoms, is there some kind of property in the electronic structure of these atoms, or have you been able to relate this to something a bit more physical, or are you staying in just higher ground?
So I actually spoke with Tony Paxton, who is a sort of, he has actually been retired for like 5 years. He's one of the tight binding generation, and they understand super well electronic structure in a very physically grounded way. And when I explained this to him, he told me, oh yeah, of course, transition metals have these scattering, you can understand this in terms of matrix elements and this. So one very important point is that this makes a cute story, but this works because transition metals are very similar to each other. If you try to do the same thing, we actually did try to do the same thing for the first row, and you can compress a little bit, but you go like from 8 dimensions to 6. You can't, because the diversity in the chemical behavior is much higher. And the second thing that I want to stress is that, again, this is very nice, but what you really would need to do, and what a graph neural network in which you associate tokens to the different species does automatically for you, is also to couple chemical and geometric information. Because typical example that I would make, a sulfur atom is an oxygen that is a little bit bloated, no? And so you can't just say that sulfur is similar to oxygen. You also need somehow to link a geometric deformation with the chemical information, which is something that in an implicit and opaque and non-interpretable and far less cute than this way, a graph neural network does already for you.
Final question from Juan.
Thanks for a great talk. So I was just wondering, I was interested in when you said that you can basically alleviate the instabilities with predicting just the forces by just basically predicting rotations every once in a while. How does this scale, like if you, well, you actually said this is not an extrapolation exercise, but if I keep like adding more and more atoms to the system, like will this make the simulation potentially more stable, or what would be considered this method?
So, okay, You mean if you have sort of a liquid, you will have internal averaging, and so in the end it doesn't matter. That's what you mean?
I'm just saying if this would always work, basically, or if I keep adding elements to my system, eventually this solution will not actually solve the issue.
I'm not sure I get the question, because the rotation augmentation had to do with the rotation equivariance, and it's not particularly affected. I mean, it's affected by the chemical diversity only through the fact that a chemically diverse model will typically be harder, and so it will be harder to learn equivariance. That was you were
maybe
asking.
Maybe we can discuss.
Okay.
Later,
Yeah.
Yeah. Thank you.
Okay. Maybe. Okay. So this is Paul will have the last word.
Last question. I wasted my early question. The multi-step or the multi-stage, for lack of better words, approach, where you showed that if you train a model where you train against energies and you train against direct forces, only differing in the output layer, being much faster. That is really intriguing. Can you speculate as to why? And you said you don't know, but
So okay, there are two things. One is it's faster because I'm getting there. Okay, it's faster because this part is faster. So here I'm plotting in GPU hours. This is as many epochs as the full conservative training. Why then it goes down so quickly? We suspect that this might be, this is something that we're working on right now. So how do these unconstrained models learn equivariance? That's a little bit the question. Because when you train against the energy, you are right, and you know this better than I, that the forces that you compute by derivatives are vectorial in nature by design. But they are vectorial in nature through the denominator, no? Not the vectorial nature doesn't need to come from the weights in the network. And so we suspect that, so one thing that we noticed is that if you train only against the energy and the conservative forces, the internal, the latent descriptors in the network tend to learn to be invariant very early on. Whereas if you ask explicitly to predict a vector, they will have to preserve some vectorial character. And this is very speculative, but it might be that by forcing it to learn a vector, you are actually helping the internal state of the network to keep higher equivariant information. So we are also trying to do this, learning also the polarizability, to see if somehow this also improves the learning behavior. So it might be that forcing the model to learn a quantity that is not just a scalar helps the model develop a richer word model. I don't know if we want to, it becomes it gives the model a more complex personality.